Hi class. I'm going to talk about mole relationships, and eventually we'll do mass calculations and chemical equations. So let's look at this. Let's look at this reaction for the formation of silver tarnish. We could say this as 2 silver atoms react with 1 sulfur atom to make 1 molecule of silver sulfide. Or we could say that 2 moles of silver react with 1 mole of sulfur to make 1 mole of silver sulfide. Some other things that we can say would include that we know this from balancing chemical equations, that the number and kind of atoms on the left and kind on the left of our balanced chemical equation in the reactants is going to be equal to the number and kind on the right. Kind, right? So however many moles of silver we have on the left, we have the same number of moles of silver atoms on the right. And then it would sort of follow that the mass of the reactants is going to be equal to the total mass of products. But what we cannot say is that the mass of silver is equal to the mass of silver sulfide. We cannot say that. And so what you're going to come to see is that we have to talk about relationships between chemically reactive species in terms of their moles. So we could say that for every 2 moles of silver atoms, we get 1 mole of silver sulfide. And so when we go from different chemical species, when we're talking about them quantitatively, we're going to have to use mole-to-mole relationships. Whether it's reactants to products, or if we're trying to figure out how much of each reactant we need to completely react, we need to use mole-to-mole relationships. And part of what I was talking about is the outcome of the law of conservation of mass. That says that in a chemical reaction, matter is not created or destroyed, and no change in total mass occurs. And so the mass of the products is equal to the mass of the reactants. And this table is just a demonstration. If they've added up all the masses on the left and get 247.9 grams, and then they add up all the mass of the atoms or mass of the products, and they get 247.9. So they're equal. This relationship, these mole-to-mole relationships, are also called stoichiometric ratios. And so with this chemical equation, 2 moles of iron combined with 3 moles of sulfur to make 1 mole of iron 3 sulfide. We can read that as 2 moles of iron plus 3 moles of sulfur make 1 mole of sulfur sulfide. Iron 3 sulfide. And these are the various mole-to-mole relationships that you get from this equation. If we are talking about reactants, we have these conversion factors, these mole-to-mole ratios, where these numbers come from the coefficients. If we're comparing reactants and products, we would say that 2 moles of iron yield 1 mole of iron 3 sulfide and its multiplicative inverse. And we can also look at sulfur and the products. So let's look at this reaction. This is called the Haber process. It's how ammonia is made industrially. 3 moles of hydrogen react with 1 mole of nitrogen to make 2 moles of ammonia. Which of these factors is appropriate? Well, this one is not right because 3 is not a coefficient for nitrogen. This one is okay because we have a coefficient of 1 for the nitrogen and a coefficient of 3 for hydrogen. And this one is not okay because of the 2. So the answer is B. And we could also have multimole factors between reactants and products. And so if we're looking for a multimole factor between ammonia and hydrogen, it would be not this one because hydrogen does not have a coefficient of 1. This one would be okay. 3 moles of hydrogen make 2 moles of ammonia, and this one has the coefficients wrong, so it would be B. Okay, so let's look at this question. How many moles of iron are needed for the reaction of 12 moles of oxygen? So 12.0, I'm going to start with what I have, 12 moles of oxygen. And I want to know how many moles of iron. So I need to get rid of the oxygen, and because I'm going between 2 different chemical species, I'm going to use this mole to mole ratio. So from the coefficients, I see that 3 moles of oxygen react with 4 moles of iron. When I do that, the moles of oxygen cancel, and what I'm left with are the units that I want, which is moles of iron. 3 goes into 12 4 times, and so my answer will be 16.0 moles of iron. Notice that these are whole numbers, and they are considered, like that, they are considered exact. So we don't limit the number of sig figs based on these mole to mole ratios because these coefficients are exact numbers. Okay, so that's showing you stepwise how to do that. Okay, now we can go from mass. We know how to go from mass to moles, right? I just showed you how to calculate the number of moles of something to react with another reactant and to give you product. But we don't measure moles directly in the lab. We use balances to measure mass. And we usually want to know how much product am I going to get, what mass of it, or how much do I need? How much do I need to weigh out on the balance to get my desired product? And for that, you would go from grams of reactant, most likely, to grams of some other substance. Could be another reactant, could be a product. And we know how to do that. We know how to go from, and in between we have to go into moles of A and moles of B. And we know how to do this, right? You know how to go from mass to moles. We use the molar mass. Then we're going to go from moles of one species to another, and we're going to use mole to mole ratios for that. And then finally we'll go from moles of whatever B is to the mass of B, and again we're going to use the molar mass. So let's look at a question. Suppose we want to determine the mass in grams of ammonia that can be produced if we start with 32 grams of nitrogen. So I have a habit of putting the relevant information underneath the equation. I think it helps me keep track of pieces of information I'm going to use. So I would encourage you maybe to consider that as a habit when you're solving these kinds of problems. So I have 32 grams of nitrogen, and I want to know how many grams of ammonia that will make. So I'm going to start with what I have, 32.0 grams of nitrogen. And remember, if I'm going to go from here to here, I have to use the mole to mole ratio. And so the first thing I have to do is convert my mass of nitrogen into moles. So remember, this is our process. We're going to go from mass of nitrogen to moles of nitrogen. Then we're going to go from moles of nitrogen to moles of ammonia. And then we're going to go from moles of ammonia to mass of ammonia. For the mass to mole ratios, we're going to use molar mass. Sometimes we're going to divide, sometimes we're going to multiply. And generally when we divide in the beginning, we're going to multiply at the end. And then this is where we go from two different chemical species, so we're going to have to use the mole to mole ratio. This is 1, this is 2, this is 3. Okay, in terms of our steps. So I'm going to go, step 1, I'm going to convert to moles of nitrogen, and I need the molar mass, and I'm going to divide by it, so it will be 28 grams. I get that because the individual mass of nitrogen is 14, and there's 2 of them in molecular nitrogen, so there's 28 grams of N2 and 1 mole of N2. That is step 1, that's what I did here. Then I'm going to go from moles of N2 to moles of ammonia. And for this, I use the stoichiometric coefficients. 1 mole of N2 is needed to make 2 moles of ammonia. So that is step 2. And I use the mole to mole ratio. Then I'm going to go from moles of ammonia to the mass. So 1 mole of NH3 is, that's going to be 17 grams. And that is step 3. Just as a reminder, to calculate the molar mass of ammonia, it's going to be the mass of the individual atoms. So it will be 14.0 grams for nitrogen plus 3 times 1.01 grams for hydrogen. And that will give me 17.0 grams per mole of ammonia. Okay, and so when I multiply this all out, 32 divided by 28 times 2 times 17, I get 38.9 grams of ammonia. I only had 2 sig figs here, so I really should say 39 grams of ammonia. Okay, and that is my answer. And that's showing it stepwise. Let's do another one. How many grams of O2 are needed to produce 45.8 grams of iron 3 oxide? Okay, so I have a target actually, so it's 45.8 grams of Fe2. Oops. And I'm going to need that's what I want. I'm going to need the molar mass for Fe2, and that's going to be 2 times the molar mass of iron, which is 55.85 grams, plus 3 times 16.0 grams for oxygen. So 2 times 55.85 plus 3 times 16, I get 159.7 grams per mole for Fe2O3. Okay, let's review our process. I'm going to start with the mass of our product, and I want to know how much oxygen is needed. So in order to make that leap from one chemical species to another, I got to first get my iron 3 oxide into moles. Then I'll go from that to moles of O2. and then from that, mass of O2. So 45.8 grams of Fe2O3. I've already calculated my molar mass, and it's 159.7 grams of Fe2O3 per 1 mole of Fe2O3. And then I need to do the mole-to-mole relationship, and that's going to be based on the stoichiometric coefficients. And then I'm going to go from moles of O2. Let me just, right, I'll cancel what I can cancel, right? Grams of Fe2O3, cancel moles of Fe2O3. So now right now I have moles of O2. And it is 1 mole of O2 gives us 32 grams of O2. And that should give us the amount of oxygen required to create 45.8 grams of iron 3 oxide. So 45.8 divided by 159.7 times 3 divided by 2 times 32 gives me 13.76. Let me see, I got 76, so 13.8 grams of O2. That doesn't, let me just do that again, just to be sure. 45.8 times 3 times 32 divided by 159.7 divided by 2. Yep, 13.8 grams.